Hi, welcome to week 5 of Fundamentals of GIS. Today I want to go over a few things related to relational databases. And this is a little bit of a complex topic, slightly technical, but I think it can actually be fun, and you've all been working with GIS already. You've looked at the attribute table in shapefiles, and so you've already been working with relational databases, even though you may not necessarily have known it at the time. So what I want to do today is actually just get more explicitly into relational databases, talk about why we use them in GIS, and give you a little bit of a sense of what you can do with them, and more broadly, talk a little bit about where the field of GIS is going in terms of this data model. This is relational databases are just one of many possible data models that could be used in GIS, and it's by far the most common one in use today in both shapefiles and geodatabases. But there are actually many possible ways of interacting with GIS data, and the relationships between different tables, the relationships between different attributes, and so on. So I'm going to talk a little bit about that. You can see on your screen right now the slide with your review questions, and I should just note that while this is up there and you're taking a look at this, that these slides are available on the Blackboard. So you can download them, take a look at them, and follow along. But I am also going to be interjecting them into this video on top of my face. So let's go ahead and get started here and start working through these slides. So first of all, I want you to take a look at this table and just familiarize yourself with it. Take a look at what it's showing and what kind of data that might be representing. And I'm going to pause for just a second, but you can also pause the video to take a look at it. Okay, so moving on to the next slide, I want to actually ask you, after having looked at this table and seeing what kind of data is in there, what are some potential problems with this database? And by problems, I mean sources of redundancy and inefficiency. There are a few things that are repeated. There are a few inefficiencies in this table. So what do you think when you look at this table? Well, first of all, I'm looking at the field for surname, and it looks like there are two Smiths, and moving on to the address field, that they both have the same address. It looks like it's probably the same person who basically made two different orders. So looking at this table, there are a number of rows, and each one of those represents a person, right? And or actually, every one represents, or does it represent a person? I think it actually might represent an order. There are a few different things going on here. In the item column, you see that there are a few CR7s, a couple CQ8s, and the address again is located right there with the surname. So there's a few different things going on here in terms of redundancy and inefficiency specifically. Each one of those people has their address recorded right there in the table. If each one of these rows represents an order, then the address isn't necessarily dependent on, isn't really necessary to record here. You can just link to that person's name and have the address in a separate table, so you don't have to keep recording it over and over and over again. Perhaps you want to also link the order number with information about the order, like the item that was ordered or the quantity. And also, I'm noticing that there are there are 4 total columns, but 2 columns for each item that was ordered. One, and you can see that when someone orders 2 different items, that it creates a separate pair of columns. That's where, and I have some circled in the slide, but that's where this lecture is going to come in handy. When we talk about file structures and we talk about relational databases, you're really asking about how to encode that information such that you reduce redundancy, reduce inefficiencies, and are able to more quickly and more efficiently retrieve information about different places and people and orders in the case that you just saw. what we just saw was a table, and it follows a structure, right? So if I put this hypothetical table up for you to see, this is a list of students. It's a file, it's a database table. And you can see here that each one of these records represents a student, and each one of those fields represents information about the student. Hopefully you are able to recognize those names. Hopefully those are meaningful to you. They are some of my favorite movie directors. But you can see here that I am just using them as hypothetical students in this database table. I'm going to add 2 more fields there just to make things a little interesting. So each one of these students now has a grade that's recorded, and they have whether or not they are receiving financial aid, and whether or not they've been caught cheating. Apparently they've all been pretty bad students, except for Woody Allen. In terms of ordering here, so in the table you just saw, they were just put in the order in which they were collected. So say a student joins a class, you just add that student onto the bottom of the table. Say a student enrolls in the university, you just add that student onto the bottom of the list of university students, and so on. That's called simple ordering, where there's really no logic behind the ordering. It's really just a convenience kind of thing. You put them at the bottom because that's just the most convenient thing, to keep adding to the list and making it longer and longer. However, there are a lot of cases when ordering might actually be really important, right? Maybe maybe you need an alphabetical list of students, or maybe you want to see them ordered by their grade. Well, this one's called ordered sequential, and I have an example here of alphabetical order by last name. I ran into a problem though ordering these because there are brothers. They have the same last name, Cohen. And so in this case it moves over to another field. Obviously the most obvious field to move to here is their first name. So they're ordered primarily by their last name, secondarily by their first name. You could also do that by grade, you could do that by their GPA, by their student number, anything that is an ordered list, that's ordered sequential. It's pretty easy to understand. So another example here that I've given you is they're ordered by their ID number. When you're working with a list of students about this big, it's really small, right? It's only 4 students in this case. But think about scaling up. Think about to a university where there are possibly 20 or 30,000 students. When you want to search for information about these students, ordering them can actually be really useful because you're able to, say you're looking for somebody with the last name of Cohen, you're able to skip down immediately to the C's and start looking through the C's to find the Cohen. However, if you're looking for something a little bit more specific that's not as clearly ordered, or maybe even alphabetical, with 30,000 students that can be quite inefficient to search through the entire database table just to find one last name and pull out that information. So in that case, we have what are called indexes. They're indices. They are basically, you can kind of think about these as indexes in a book, really. It's really easy to understand. So how does that work, right? In a book, say you have a book and you need to find all the occurrences of the word. I'm just going to reach over here. So I reached over here and I've grabbed Doreen Massey's space, place, and gender. And I want to find all the uses of the word
feminism.
I want to find all the uses of the word feminism. And so I go to the F's in the index and I see that feminism is on pages 7, 12 through 13, and 119. So because I know that, I can just go to page 119 and there is feminism. So think about it this way. If I didn't have the index, and I needed to find all the uses of the word feminism, how would I have done that? I would have needed to literally go to the very first page and read through page by page by page by page, underlining every use of the word feminism as I go along. And I would not be able to quit until I'd reached the entire end, the entirety of the book, the very end of the book. And then I know that I've seen all the uses of the word feminism. I don't have to do that because I can go straight to the back. The index points me where in the book, to where in the book the word feminism is used. That's how an index in a database works. An index in a database basically just points us to where we can find the information that we are looking for in the database without having to start from the very beginning and work all the way through until the very end of the database. It makes it much more efficient, especially when you get to the larger databases. So in the case that you see here in the slide, there are 4 students. Here, an index is completely useless. It doesn't help us at all. But when we work up towards 20, 30,000 students, even much smaller than that, it makes a big difference in efficiency, speed, and lower use of resources. That's what databases are. It's a collection of these tables and indices and a way of collecting and organizing and structuring data so that it's easy to store, manipulate, and retrieve. Database management system is the software programs, software packages that help us do that. However, instead, in a relational data model, when tables and data are organized according to the formal relational data model, instead of thinking about these as rows, instead of thinking about these as tables, we think about these as relations. The records, the rows, are tuples. They're collections of information about whatever is being observed. A student, an order online, or a person in general, those kinds of things, or a place. The fields are called domains. Those terms are not super important to know for this course, and to be perfectly honest with you, they're not really necessary for you to be a very effective and very good GIS practitioner. However, I do want you to be familiar with these terms, because when you start working more in the more advanced GIS classes, in the more advanced CS, computer science courses, or even in some of the intermediary courses, those terms you're going to see those terms come up, and I just want to make sure that you've been exposed to them. Not important right now for you to memorize them and know all the details about what those mean in a formal sense, but just know that there are these things called relations that we think of as that are tables. Tuples are the rows, and domains are the columns or the fields. So we have a relational data model where we have a series of students. Eventually, if we keep building this out, there's going to be some duplication. That's going to be a problem for the relational data model, because every row has to have something that distinguishes it from every other row, something that makes it unique. We call this the primary key. The primary key is basically that. It is the field in the table that is going to distinguish every single row from every other row. It only has to be one field, although it can be more than one. But this is basically the field that is going to make sure that every row is distinguished by other rows somehow. In this case, what do you think the primary key is? Well, the primary key in this case is the ID. Because it can't be last name because there's a duplicated, it could be first name, but it's probably better to go with the ID because that captures the entire student, not just their first name. It cannot be the grade because B is duplicated. This primary key is the field that enables you to join information from other tables. It helps you link with further tables on. So if you have a table about students, but you also have a table about all the courses that they've taken, you don't want to put those together necessarily, and we'll get into why in a little bit. But the primary key is going to enable you to link with different tables. Tables about the courses that they've taken, tables about their financial aid status, tables about their personal lives, if you have information on that. That'll be a little creepy. But we're looking at here at a join to the courses that they've taken. So we see here that Woody Allen has taken Geography 6062. If we want information about Geography 6062, we would link to the classes table, a table of the classes, what the enrollment is, who the instructor was, what the purpose of the course was, the number of credits it gives you, all that information would be stored in the classes table, a table about the classes. In the student table, you see which classes that they've taken, so you're able to link with those other tables. You do that with, in this case, what we call the foreign key. One thing that's important to know is that every table has a primary key. It is necessary by definition of the relational data model to have a primary key in your table. Something that distinguishes all the rows from each other, again. So in this case, when you need to link up with these other tables by virtue of the relational data model, you have what's called a foreign key. And that foreign key is specific to your table, but it is what is going to be used to link to the other table. It's going to be what the software, the relational database management system, looks for in the other table to enable to bring over that information. So in this slide you see here, the foreign key for student is which course they've taken. And because you have the course name there, you're able to go over to the courses table and retrieve information about that course. Notice that the foreign key links with the other table's primary key. And you can keep linking these up, and that's one of the great things about the relational data model, is that you can keep making these linkages. You can make a system of links that is so vast and diverse that is beyond imagination. Here, you can, for example, you can see that perhaps there's information about the instructor, which office they're in, what their email address is, how many courses they've taught. For each of those, for which office building they're in, and then you might be able to link with information about the office building. So I am currently in Gladfelter Hall at Temple University. This building has a bunch of attributes that might be interesting in some cases. The architect who built it, the year it was built, the status of its code violations might be of interest to me. A lot of information about this building that, because I have linked from the student to the class to the instructor, we can also link to the office building, we can link to information about Philadelphia, whatever it takes. That's what joins are about, linking information from different kinds of tables based on these connections between the foreign keys and the primary keys. I want to take a pause here and just note that we're shifting a little bit. These redundancies and inefficiencies that you saw in the first table, those are redundant and inefficient, but we have a specific technical name for those redundancies and inefficiencies. Those are called normal forms. They're basically rules, regulations, blueprints for how you're able to create these relational data models, these tables. They're the rules for how we set these tables in order to reduce these inefficiencies and redundancies. Those are what normal forms are. And there are three that I want to talk about right now. If you know one of these three, I'd love to hear about them. But these are three that are really good starters for proper storage, collection, and manipulation of your spatial data. This is going to help you reduce redundancy and efficiencies in your shapefiles and attribute tables. So you can see here that I have this list of students with their grade and their class. So Woody Allen got an A in my Geography 6062 class, which is the doctoral level GIS, Fundamentals of GIS class. He took my other class, Digital Mapping, Geography 0821, and also got an A in that course. However, Joel Cohen found out he likes college a little bit too much. He got a C in Geography 20, but then took my Geography 6062 and did very poorly in it. I was not okay with that. He was a very bad student in that class, and I refused to let him pass with credit. So he got a D. His brother, on the other hand, a stellar model of what a student should be, showed up his brother quite a bit by taking another class, Geography 90, and doing better in that one than in his first class. He got an A in that one. Wes Anderson was friends with Joel Cohen. They were buddies and each other's sources of information on parties. So just like his buddy Joel, Wes did more poorly in his second semester. But on the other hand, this one was in Math 100, and to be honest with you, I'd probably get a C in that class too, so I can't really blame him. Those two fields, grade and class, violate the first normal form, which specifies that there should be one value per field for each record. It violates that, and that's a bad way of organizing information for a lot of reasons, not least of which because if we were to keep adding classes onto this or pass it on to someone else, they would have no idea how to decode this, right? We know, because we just saw how this unfolded in real time, that the for Joel Cohen, he got a C in Geography 20, and then a D in Geography 6062. However, someone passed that off to someone else, and they're not going to know which applies to which. So it's a bad idea to do that, and I will pause for just a second and ask you how you think we would be able to solve this problem. What kind of organization tweak might we make to get around violating the first normal form? Pause the video. And welcome back. I would say separate this into different columns. Perhaps you could have a separate field for every course that they take. Course 1, Course 2, Course 3, and so on. Still a little inefficient, but that's one way of getting around it. This no longer violates the first normal form. You could also have Course 1 name and link with the course description and so on. And you could have all kinds of information that adds on to this. But right now, we're looking at a solution to the first normal form. The second normal form specifies that non-primary key fields must be dependent on the entire primary key, and not only on part of it. So I mentioned that primary key is usually a single column. However, it can be more than one. If we wanted to use the student's last and first name as the primary key, there's really no reason not to do that. Makes sense in a lot of cases. In the slide that you see on the screen right now, we have not just their first and last name, but also their progress through college, the year that they are in school. So Woody Allen has been there the least amount of time, and Joel Cohen has been there the longest. Notice that grade, we'll assume this means GPA, grade is dependent on the student, but has nothing to do with their year in school per se. In other words, the link to what is important in this table is their first and last name. The year is going to keep changing, and that has nothing to do with, per se, their identity. The only way that it would is if there were two Woody Allens and they were different years in school. If there was some kind of a rule, a formal university-wide policy that says they cannot admit more than one Woody Allen within a certain number of years, that would be the case when that would be useful. But let's just assume that that's not happening here, and instead Woody and Allen should be the primary key, Joel and Cohen, Ethan and Cohen, Wes and Anderson. Grade depends on the student, not on their progress through their program. So pause for a second. How do you think we might be able to get around this violation? Just to be clear, what's happening is that the violation is happening because the grade and status is dependent on part of the primary key, the first and last name, not on the entire primary key. So we would separate this into different tables. Maybe the student's information about the information about the student is in one table, but then how to interpret those years in school is a separate table. So first, year 1 means that they're a freshman, year 2, sophomore, and so on. Separate that into a different table, and now grade and year depends on it depends on the entire primary key and not only on part of it. The third and second normal forms are a little bit difficult to tease out conceptually for students who hear it for the first time. Once you get it down, it's not a big deal. But the second and normal form are distinguished by, they both relate to the primary key table, and that causes some confusion sometimes. The way to remember this is that the second normal form specifies that each non-primary key field has to be dependent on the entire primary key, not only on part of it. And the third normal form specifies that the non-primary keys should be dependent only on the primary key field and not another field as well. So if there's information about a course, for instance, a course that a student has taken, the information about the course should not be in that table. You see that happening here in this table, where there's information about the students. Each one of those rows is a student, right? And so each of the fields should be information about the student and not about anything else in the row. The primary key here is ID, and the ID is information about Ethan Cohen, Wes Anderson, Joel Cohen, and Woody Allen, as is the grade, and as is a course that they have taken. However, instructor is not about the student. It's about the course. And in that way, it's dependent on the class and not on the student. It's dependent on a non-primary key field. Pause for a second. How do you think we might be able to fix this? One way is to separate that out into a different table. Information about the course goes in one table, information about the student is in a different table. If you want information about one thing, it's in a different table. Information about another thing is in a separate table. This makes a lot of sense, right? If you are trying to retrieve information about students, you don't really care about who taught the course. You can link to that by looking at the classes that the students have taken. But the information about the course should be its own table completely. So we move on, and we have a lot of violations in this table. We violate the first normal form, we violate the second normal form if that includes another field like grade, for instance. And we violate the third normal form. Take a second to think about why each of those normal forms is violated in this table. And think about why it might make sense to fix those violations here. Some of the reasons that I can think of when looking at this table are that if the instructor for a course changes, the class will have to have, every class in the entire table will have to have their instructors' names changed. This actually happens a lot. An instructor is slated to teach a course for the fall. They get a job offer at another university and they move there. Now all of a sudden the university has to find a replacement instructor. Instead of having to go into all the students' records and change the instructor of the course that they're going to be taking in the fall, you are able to just update one table, and then automatically all the other tables are updated as well because they're linked dynamically. They're only pulling in information when it's requested. When you ask it what is the instructor for the course that the student is going to be taking in the fall, it's updated automatically by updating a single table of the courses and their attendant instructors. Also, every time a student changes their class, say they unenroll in one course, but they stay enrolled in the university in other courses. Every time a student would do that, you'd have to go in here and figure out some way of parsing out the different classes, the different kinds of the different instructors that they have. You'd have to parse out all that information. That would be a really messy process. Instead, what you're able to do is have a list of a set of fields of the courses that the students are taking, and have that linked to the instructors. And update those fields individually. If a student unenrolls in one course and re-enrolls in a different course, you just update that student's records. Not a big deal, but it would be a big deal if those normal forms were violated. Now, lastly, I just want to spend a minute thinking about where databases are going. Like I said at the beginning, the relational database model is by far the most commonly used data model in GIS today, and it's partly because that's the form of data structure that's used by Esri software. Shapefiles use it, geodatabases use it. However, that is not the only file structure available to GIS practitioners. There are a lot of other formats that could be taken, and there are a lot that are quickly gaining ground. And this is pure speculation, but I see the ways that these databases and data structures are changing GIS, and I have to think that in 10-15 years, we're probably going to be moving away from the relational database model, or at the very least, non-relational database models will proliferate in ways that we don't currently see. In this way, databases are quickly changing in GIS, and there's a lot of dynamism in the field. Things are moving very quickly, and it's a little bit fuzzy where things are going, but I want to speculate just a little bit about where this is going in order to situate relational database models within a broader spectrum of how data can be collected, organized, and stored. And by doing this, I want to actually the reason I'm doing this is because I want to stress a range of different possibilities. When I tell you that data is stored in the relational database model, I don't want your brain to shut down and think that's the only possibility available to us. I want you to think broadly about what is excluded from that database model. What can we not include in the relational database model that we might be able to in other forms? Unfortunately, since this is not a class on computer science, this is not a class on database management systems or process practices, I can't really get into a whole lot of detail on this, but I just want to, again, situate relational database models within a broad spectrum of possibilities. So first of all, there's the relational part of relational database models. And on the spectrum that you see on your screen right now, geodatabases and shapefiles are probably, I would say, somewhere between MySQL and Oracle there. Certainly between MongoDB and Oracle. On the one end of the spectrum, you have databases where there is nothing other than the relations. The tables are themselves what constitute the databases. On the other end of the spectrum, there are no relations. It's all messy, it's all jumbled. It's just collecting information as it comes in. The forms, the structures are not determined beforehand. It's dynamic. It's determined in real time by the data itself. On the non-relational database side, we have things related to big data, to social media, that kind of thing. There are also the schemas, and this is very much related to relations, but more about the structure of the data. It's more about the what's going to be allowed in terms of the fields, the columns, the attributes that you can give spatial data. So on the one hand, you have the geodatabases and shapefiles, which are more towards the bottom of the spectrum you see on your screen. Again, somewhere between MySQL, Oracle, and Cassandra. And what's important there is that you know what the structure is going to be beforehand of your file. You know what attributes are going to be important and which ones you're going to not include in your database. On the other end, you have, again, the structure of the data being generated dynamically by what's collected. So if I go to Twitter, for instance, I don't know beforehand what someone is going to say in a tweet. I don't know if the tweet is going to include a picture. I don't know if it's going to include a link. I don't know if it's going to include a video or a GIF or what it's going to include. So I need to be open to everything. In a Facebook message, I don't know if somebody's going to write an entire novel in a reply, as I kind of tend to do a little bit too much, or if somebody's just going to put an emoticon and click send. I don't know if someone's going to include a link to a news article or a YouTube video. So in a lot of cases, it makes sense to have a schemaless database structure. On the other hand, with a lot of geographic information, especially some of the more formal kinds that are used by the Census Bureau, the USGS, and so on, you need to know, they claim that you need to know the structure beforehand before you start collecting data, and all the data that is collected needs to adhere to that database structure. There are lots of reasons that that is a problematic way of approaching geographic data, and I would invite you to think about why that can be problematic. And the last thing that I want to just quickly touch on is the fact that in Lab 1, you took advantage of the two kinds of questions that you can ask GIS. In Esri's software, you're able to do you're able to ask ArcMap, two different kinds of questions. You're able to ask questions related to what kinds of attributes are associated with objects, places, people, things. You're also able to ask about spatial relationships between different objects. With both of those questions, you are performing what's called a SQL query, Structured Query Language Query. The word query just means a question. So you've already been conducting SQL queries, even though you didn't know you were doing it at the time. With the attribute query, you're asking ArcMap to go in and row by row, for every row, go to the field that you specify and check if a certain criteria is met. So you see here, in a list of states in the US that have a field called sub_region, and each one of those states has a subregion. There's the Midwest, there's the West Coast, there's the South, and so on and so on and so on. Well, as you did in your first lab, you're able to go in there and say, for every row, for every state in this case, check if the field attribute of subregion is equivalent to NENG, New England. You perform that you perform that attribute query, the SQL query, and the states that have that attribute are returned positively. They are selected. Well, you might notice in the select by attributes box, just above the part where you type in, that there is a little bit of text there. It says select asterisk from states where, and then colon, and then you start typing below that. So this is all part of the SQL syntax. It's the structured way that you ask these questions of ArcMap. And it's structured pretty simply, where you specify a set of fields, one or more, and a table that you want to ask the question about, and you specify a condition that needs to be met. The tables here refers to the shapefile or the layer, the geodatabase. But this is more broad than that. You can conduct SQL queries structured in this way on any sort of structured data table. So looking at the geography classes table there, if we wanted to find out which classes were taught by instructor Burns, we would perform a SQL query. We would say, we want to check which of these classes were taught by Professor Burns, and we want to have a certain amount of information returned to us. So say we're just interested in the class name, because we already know the instructor's name, so we just need to know the class name. We need to know the classes that are taught by Instructor Burns, to repeat myself a little bit. The select part of that syntax is the field that's going to be returned. So we want to return class, so we would say select class. We want to specify which table to query, in this case it's geography classes, so we would say select class from geography classes where, then we specify the condition being instructor is Burns. Writing that out here, select class, you can also return instructor if we want to, but in this case class is more important. Select class from geography classes where instructor equals Burns. Going back to our attribute query from above, we specify that we want to return all the fields from states, the state shapefile, where the condition is met, where subregion, the field subregion equals New England. A second attribute query, we can specify two criteria to be met. We want the subregion to be New England, and we want only states where the population is above, 5 million, I believe? In other words, two criteria have to be met to be returned here. If we just go with populations over 5 million, it would give us Texas, California, Florida, New York, and Illinois, maybe a few others. Many others, actually. But since we're not asking just about the population, we're also asking about the subregion. It has to satisfy both criteria that we said. In that case, it's only Massachusetts. So in that case, we are working with more than one criteria, and the end term there is a little easy to understand. We want to match two criteria, and both of them must be met. However, there are cases when we might want to say, we're not really sure which is going to be most important. We have two criteria, but we kind of want the states that meet both criteria. There are other cases when we might want to reduce the number of results that we get by specifying that we want states that meet one criteria, but not another one. So give us all the results of this criteria, but then subtract from that the states that meet this other criteria. Let's look at what each of those mean. if we have this accurate table of parks in Philadelphia, we want only parks with with any benches at all, so more than 0 benches, we would say select from this table select all the fields from this table where the criteria is met, benches is greater than 0. Which records do you think would be returned by that SQL query? It would be all of them actually, except for number 5 and number 7 there. Another question here. Select records with more than 0 benches and where the primary use is dog park. How many would be returned here? Just one. Just one, number 3 there. Because while there are lots with more than 0 benches and a couple with dog park as the primary use, there's only one that actually meets both of those criteria. Select records with the primary use equals tennis court and the primary use equals dog park. How many will be returned? Well, 0, because none of them meet those criteria. In fact, none of those have more than one primary use because they do not violate the first normal form. So this one will not return anything. The next question. We are interested in 2 kinds of primary uses of parks. We are doing some kind of a project where we are going to be doing an analysis on dog parks and tennis courts. I'm not sure what kind of project that would be, but let's just go with it. We want to get information about the records of the parks that are either tennis courts or dog parks. How many would be returned by this SQL query? Looks like 3 of them. Numbers 2, 3, and 7. Those are the parks that meet either the criteria primary use equals tennis court or primary use equals dog park. Now think about this, just to explain one thing. There are lots of cases when all of these will be useful. Say we're interested in states on the margins of populations for whatever kind of reason. We are not interested in the mean population states. We're interested in states that have either very few people or very many people. Say we want to do comparisons of healthcare costs. That is an OR operation, right? We want to know either the states that have very few people or the states that have very many people, and not the ones in the middle. Say we want states that have a lot of people, but are primarily, I'm not sure off the top of my head, primarily vote Republican. In that case, we could specify, we could do it 2 ways actually. We could say populations that are high and populations who voted Republican, or we could say, if only 2 responses are recorded, Democrat and Republican, we could say states that have high populations, but not those that voted Democrat. That's another way we could do it. There are a few cases when that could come in handy. We could say, if many responses are recorded for voting affiliation, we could say populations that are very high and not populations that voted either Democrat or Republican. That's an interesting question to think about. Lots of cases when each of those would be useful, and I would be happy to entertain your ideas regarding that. I have a series of 4 questions, 4 prompts at the end of the PowerPoint asking you to write SQL queries that satisfy the following questions. How many parks have 2 or more benches? How many parks have a garden and at least 1 bench? How many parks have a ballpark or a tennis court? And how many parks have a ballpark and a tennis court? Think about that, maybe run through those on your own. I actually have an in-class exercise that we'll mess around with next time we meet. Let me know if you have any questions about this material. You can leave it in the comments below. You can email me or bring it up in class next time we meet. I hope this was useful, and I will see you on Tuesday.